Hello. Okay. So today we are starting our next kind of, you can call it, algorithm or next idea, that is CNNs, that are convolutional neural networks. And we're going to talk about how they have revolutionized the field of image recognition, image classifications and segmentation. All these things will come in picture. So, so in the last sessions, we actually tackled how to classify an image that has like pixels, right? Every image is made up of pixels, and you are trying to uh, somehow classify them using those pixels. Now, what you essentially have is flattening the pixels into one single, array, and then using that array. In the last sessions, we have talked about a situation where we had 5 by 5 image and we flattened them, so it was an array of 25 pixels, and we trained those 25 pixels on a neural network, right? But if you noticed, as we are flattening the whole thing, we are losing a lot of context. We are losing, because images are not like just random numbers, right? They are have a place uh, uh, in the image, and every pixel is denoting something, and they are related to other pixels around them, right? So what happens is, in those simple algorithms like ANNs cannot really capture the essence of a picture, right? So we come up with an solution for that, and that is what we call the convolutional neural networks, where we are taking features as a bunch of filters, right? And we are doing the feature extraction through those filters. We will talk about them. Let's not jump ahead of ourselves. So in the last chapters, we talked about pixels are as features, and we consider each pixel as an individual and independent feature, right? Thus losing information while flattening the images. We also talked about weights as pixels. So if you remember, uh, weights as pixels is something. So you can think, now our whole thing, from neural network is going through them, and we're getting the output here, right? These are the pixel values coming in, 25 of them, and we can think of these weights also as pixels. If you turn these, because you have these weights coming in, right? You remember, uh, we can think of pixels as uh, features, and we can also think of these weights as pixels, and how they are changing over when the training is happening, right? When we are doing this back propagation and we're changing the weights of it, we can think of these weights that are there as nothing but as pixels. Sorry about that. uh, Give me a second. Yep. Yeah. So now pixels can be thought of as weights can be thought of as pixels, and and we can simply make this case that how are those numbers changing in those weights, and we can represent them as pixels. Okay, so how we could interpret the weights used by a neuron as an image, and more specifically as a filters. Okay, now it's time to let's talk about the convolution. So in convolution is a mathematical concept in itself, which basically is a mathematical operation on two functions that produce the third function, expressing how the shape of one is modified by the others. We're gonna have explanation about that. Okay, in image processing, a convolution matrix is also called like kernels and filters, and typical image processing operations like blurring, sharpening, edge detections, and more are accomplished by like performing these convolution between kernels and an image. So we'll know what convolution is. Okay, so filters and kernels. One definition of filters is like uh, it applies these filters on an image. Usually the filters are small square matrix. The convolution itself is performed by applying the filter on image repeatedly. Let's try a concrete example. Okay, so you see this image here, right? I hope you can see this. So this is your actual image, and these numbers are, let's say, the pixels. Okay, and so if you think about it, this is an one image with one channel, and it's 6 by 6, right? 6 by 6 image pixels, that is 36 pixels are there, and you have this filter or kernel, or kernel or image, whatever you call it. Okay, and what you're doing is you are actually putting this filter on the image. So it's a 3 by 3 filter as of now, and what you do is you convolve them. What do you mean by convolution, right? You will take, multiply every single pixel with the corresponding pixel, if you are keeping that filter on top of the image, right? And you will multiply it, so the first pixel would become 0 into 5, the second pixel will become 0 into 0, something like that. Yeah, so you have this big picture. Okay, and I'm just taking this part of it. Okay, and you're taking this filter that is a 3 by 3 filter, and you are superimposing it on this. Okay, you superimpose it on this one, and you multiply this value with this value. So the first case what we have here is, as this filter is, this is what we call identity filter, because it will not change. So think of this like all the other ones are zeros here, right? Only this one is there. So you multiply this, okay, so let's do this. Multiply this by that, and you will get 0, and this by this also 0, 0. All of them are 0, only this, the middle part, that is 9 and 0, 9 and 1 will get 1. And what you do is you keep adding them, 0 0 0 plus plus, only 9 will be added, and you convert all of that into one number, that is the addition of all that, that is 9. That's it. That's what you got out of it. Okay, now what you do is take the same picture, you have the same picture, and you take the same filter, but here what you, instead of using the first of them, you, let's say this is 6, right? 1 1 2 3 4 5, and 1 2, oh my god, 1 2 3 4 5. You, instead of this one, you take this one. This is your new kernel now. Okay, you superimpose on this part and do the same operation. So if you check this out here, the value is 0. Oh my god, the value is 0 8 7, and starting from there, right? So again, I can easily say it's 0 8 7 9 and all that stuff, because all, and we take that kernel and multiply it here, and what you see is, if you do the convolution, with the this matrix that you have, you will get, you have already got that one pixel here, right? That's 9, stays 9, and this one will just be 5. So here it will be another one, that is 5. Okay, you do the same thing next time. So that is what we call convolution. You are going through superimposing the kernels or the filters on the image, the actual image, and keep on going over and over again and get these things out. Okay, cool. So these filters are trainables. Okay, these are initialized randomly when you are in the network. When you start off with the training process, it does by it all. The initialization are done by PyTorch itself, right? And these are trainables that you can actually train in through backpropagation. Okay, we are not going to talk about backpropagation using in the CNN, because it's kind of hard and a lot of variables are going in, but the principle still remains the same. Cool. So that is what we have as filters. Okay, okay, so you see in this image the gray area on the top left corner of the image, which is the same size as a filter. That's the region to which the filter has been applied and called the repetitive field, drawing an analogy to the way human vision works. Moreover, look at the shape underneath the image. They follow basically NCHW, that is N is the number of image, C is channel, H is the height, and W is the width. I have already shown you that right here itself here. However, look at that's fine. Finally, the asterisk represents the convolution. So this asterisk is actually a convolution operation, okay, mathematical operation in a sense. Let's build one. So this is an numpy array, and we build one here. You can see I know there's just one image, so it's just one here, but why we are keeping it the 4-dimensional is that eventually we will move to multiple images, and we want to get comfortable with the way images are represented mostly while training and creating data sets and stuff, right? And this is what you call identity. This is the filter kernel. You see the numbers are identical. So that's that. Okay. Now see the convolving areas, right? The first area that you see, the first gray image, this one, right? And you're taking the image and you're multiplying with each other, and you got add up to 9. So that's what it is. So you see it becomes 9 here. Okay, cool. Let's do that. So you can see the total. So what this operation is doing is taking the single is what? Single is your single image, and entity is your identity image. You're taking all of the first dimension, all of the second dimension, that is all the image, all the channels. As of now, that's just one channel and one image, and you're going from the first to third, right? First to third row and first to third column. We're taking that region, so it will be this region that you see, and the filter region is simply we are doing multiplication. So this is what we like element wise multiplication, right? And then you are summing up everything, and you get 9 out of it. Pretty cool. Okay, now moving over, we can keep moving this from convolving over the first to the convolving over the second one, right? And move region one step to the right, and do it for this guy. It will be 5. So if the new region is moved, okay, and let's do it for this guy, and that's 5. Add up to 5, right? So next guy is 5. You can see that same operations happening here. Okay. Okay, now what if right, if it does not go beyond this, okay, it will just stay here, and once it's done with this block, it will move to the next block, that is here, one by one. Okay, I hope that makes sense. Okay, I think that is what we are showing here. If we move too much, it will just throw an error because there is nothing to multiply from. Here it's empty. Okay, cool. Yeah, so there's a kind of a problem with multiplication because element by multiplication requires you to have the matrix of same size or shape, you know. Okay, so this is the formula. We're going to talk about it in some time. So I hope this much is pretty clear, and it's pretty simple to understand as well. It's very intuitive. The good part about CNN is it's kind of intuitive, and you can actually see what these filters are learning in the process, right? Cool. Okay, let's talk about how these size of the filters affect the output of the filter. You can clearly see that the input was a 6x6 matrix, but the output right now is a 4x4 matrix. That is, the size of the images has been reduced. Somehow we did that using the convolutional the kernels or filters, whatever, right? The larger the filter, the smaller the resulting image. That's a very important point to have, that if you increase the size of this image, you will have a smaller size of the filter, it will have a smaller image as an output. Okay, and this is the formula that you have. So here the formula is simply that of I will put this in. Formula is saying that h of I and w of I, that is height of the image, okay, if you convolve it with the height of the filter and the width of the filter, right? This is the image and this is filter, right? You have this simple formula that states that height of image minus height of filter minus 1. Okay, hit this part, and the next part is, so this is the input part, and we are trying to find the size of this image, that is the output image, right? And this whole part would be the height of the output, and here it will be the width of the output. So wi minus wf minus 1, and this will be your width of the image. Okay, I hope that's clear. Now I can put this in. Okay, so in the first case, what we have is a 6 by 6 image that has been convolved by a 3 by 3 filter. I can just plug that in. So what's the height of the image? It's 6 minus height of the other is 3 plus 1. Okay, this is the first part, that is your height part, and this is also the same, right? What's the width? 6 minus 3 plus 1. So you got 4 comma 4, right? So the output you get is 4 comma 4. The output image will be 4 comma 4. That is the formula that is given here. Okay, so kernels are mostly square matrix, so we just write it by f being the size of the square matrix, right? You just need to tell once that it's a 3 by 3, 4 by 4, just call it 4. Okay, and you can simplify the whole formula into this, right? This is the height and this is the width. I hope that makes sense. Cool. Convolution in PyTorch. Before getting there, do I have to go through anything? Let me see. Okay. Now there are few ways to keep this. For example, if you don't want to change the size of the image from 6 by 6 to 4 by 4, it's changing right now. Okay, if you don't want to do that, what you can do is they can add padding into the image. We will get to that part. Okay, let's say if you increase the size of the image, that's the kernel image, right? If you have the kernels and you're increasing the size of it, if it were mostly they take it as 5 by 5 and odd numbers. The square matrix is always an odd number for the filter. So if you have a 12 by 12, let's say, image, and you are doing it over a 5 by 5 filter. Okay, so if you see, what you have essentially is 12 minus 5 plus 1, right? 6, so 6 by 6, the resultant is 6 by 6. Okay, cool. I hope that makes sense. If I change this to 7 by 7, let's say, in this case, okay, so you have, as I said, if you increase the size of the filter, the image gets smaller. So it's 12 minus 7 plus 1, that is simply a 4 comma 4. So you can clearly see, as I increase the filter size, the image has dropped, right? The size of the image has dropped, sorry. Okay, let's talk about how PyTorch does this. Okay, in PyTorch, now that we know that how convolution works, right, let's see how PyTorch does this. First, we need to convert our image and filters to tensors, the same process that we did, because we just initialized it using numpy, right? Let's turn them into filters, right? Since kernels and filters are used interchangeably, the word actually, especially when it comes to arguments of different methods, so I'm just going to call them kernel identity. Okay, even though it is exactly the same identity filter we have used so far. Just like the activation function, right? Convolution come in two flavors, that is functional and module. So before the last session we talked about activations, and there were two ways to do that, right? Using the module function modules, that is nn dot something, and using the functional, that is f dot something, right, in PyTorch. So there are two ways to do convolution as well. Okay, so there is a fundamental difference between the two though. The functional convolution takes kernels filters as an argument, while the model has learnable ways to represent the kernels. So functional module, that is in functional what would you call it, right? The functional way of doing it in the PyTorch, okay, they just have a kernel. You can tell the size, what is the size of the kernel or something, or actually have the whole kernels and just pass it the image and the kernels, and do some specific and show some specification, and it will show you what happens. Basically whatever we did here, it can show you that. Okay, but the module part, that is nn dot something, right? You remember, see the nn dot something, this part actually we have input channel, output channel. So here the way here it initializes the weights so that these filters are learnable in the backpropagation. Okay, so input channel is, we define input channel depending upon the image that we are giving. If it's a RGB, the input channel would be the in channel would have uh, let's say 3, and the output channel would be the number of channel you will define for yourself, that this is the output channel that I want. Okay, so that is a hyperparameter in itself. And the kernel size is 3 as of now. We are using just 3. That is this size, right? This is the kernel size. Okay. Kernel size is defining the shape of it. As it's a square matrix, we just say it's 3. Okay. Now both of them have been tensorized, if you can call that. Okay. And let's try it with F model, right? That is functional. And we got the same answer, 9507, all that's 9507. We got it, right? It's pretty cool. We are just passing in the image and the kernels as it is. Cool. But now with NN, there is this is a conv2d. Let's see conv2d PyTorch. It's always good to go through the documentation once at least. Okay. Yeah, here we go. So the conv2d is a 3D one. Okay. Let me find conv2d if I can. Okay, just so you know, this is the module that we are mostly coming up with, right? We have used a few of them, like the nn.linear ones. You remember linear ones? You can go inside and check for yourself. This is nn.linear that we had. There are many more identity, and this is the operation they will be doing bilinear, and so many of them are there, right? Pretty cool. And loss functions also is there. nn.mse we use for regression, and BC binary cross entropy. This is, you know, KL divergence, and lot many losses. They already prepared it for us. I mean, you can use them if you want, but let's just talk about the main part of it all, that is convolution layers. And we have con2d, that is basically working on 2D. So what you say, in the simple case, the output value of the layer in the input size, that is this, and the output will be something this. So in this case, our input is 1 comma 1 comma 6 comma 6, right? If you change the number of outputs, so it will convert this whole into this. So the operation that is happening is, so ni being the whatever the number of whatever is the uh, output, yeah, the image number basically, and C out is the channel output, right? Cool. Give me a second. Okay. Yeah, and the bias is there, and we are doing a weights. The size of the weight is basically channel versus the k being the kernel size. Okay. And the input, we are doing a convolution. See, you see the star over here, that star is denoting that it's a convolutional operation happening. Okay, star in 2D cross correlation operation, cross correlation operation, if I am not wrong, that is same basically the uh, convolution cross correlations. Okay, yeah, basically it's convolution operation, right? Okay, cool. Yeah, strides, there are few parameters that you have to look into. The in channel I have told you, out in channel is the number of channels coming from the image, out channel being the channels that you want is a hyperparameter. You can change it. The kernel size or hyperparameter, you can change it. Stride is basically how we will be looking into it, but I will just give you a brief on that. Stride is simply saying that how the jump will happen. Right now we are moving one block at a time, one like block at a time, right? It's going from this block to this block and then this block one by one. But what if we do stride equals to 2? It will jump 2. So it will start from here, and next kernel convolution will happen here. Okay, that is how simple it is. So it's like instead of going from this, instead of going from this to this, right? So it was like started from here and it went here. Instead of that, what we can do is, if stride is 2, it will start from here. This is the first one, and the second one will be here, right? And the third one, as it cannot jump 2 times, so it will go back here, but here also it will be coming down here, not on the second line but here. Okay, I hope you can understand that, something like that. Okay, that is your stride. And what else do we have? Stride is there, the padding is there. Padding is like adding layers on the image that you have. Okay, so you will add more layers, adding, in the sense, you see this image, instead of, we will add pad 0000 here on the top of here surrounding the image. We will add that, so that if we do that, we will get an image of the same size as the input image. The output image will have the same size as the input image, given the kernel is same. Okay. Okay, dilation is something that I rarely play. We can control the space between the kernel points, also known as the a torus algorithm. It is harder to describe, but this link will nice visualization of dilation. Okay, there's actually pretty good visualization as well, I bet here. Yeah, you can see. Check this out. So this is what we call, so this is the image, and this is the filter 3 by 3, and this is the output. Okay, this was a 4 by 4, and the filter is 3 by 3, and if you put it in the formula, if you remember, it will be 4 minus 3 plus 1, sorry, yeah, 4 minus 3 plus 1, that is 2 by 2. So we got a 2 by 2 output. Now this is what we call padding. You see, this was the actual image, that is a 5 by 5, and you are adding these 0 on it, right? Got it? Now if you think this, it's a 4 by 4 filter at the same time. So no padding, this one is no padding, no stride, arbitrary padding and no stride, right? We randomly added 2 more padding on all over the image, right? And half padding is basically adding 1 more pad. So if you see, now the 3 by 3 matrix is there, that is your kernel, and the image size is 5 by 5. Because of the padding situation, we have an output that is also 5 by 5. I hope you can appreciate that fact, right? And full padding and with no strides. Okay, cool. And now let's look at no padding with strides. So see how it's jumping. I showed you how it's jumping. If start from here, then goes on the next part, right? That's what we call strides. It's stride of 2. Here padding is there also, and stride is also there. So you can see how that happens. Stride is there. Stride is an odd number, I guess. So check that out. I hope you can appreciate this. Transpose, convolution, animation. Okay, no padding, no stride, transposed. Okay, dilation, we're talking about dilation. Okay, this is what dilation, convolution. So basically, it's like taking your spacing between your in the kernels. Actually, if your dilation is 1, that means every pixel will be like this. There will be a space between them. That's what it's trying to explain. It's much harder to understand that, right? It's spacing between the kernel points. Spacing between the kernel points. That's what we see here, right? Pretty cool. Yeah. Okay. We went through a lot of group controls. The connection between the input and output must both be divisible by the group. For example, at group 1, all inputs are convolved to all outputs. Group, the operation becomes equivalent to having 2 conv layers side by side, by each seeing half the input channel and produce half the output channel. Oh, okay. Never really tried it, but I mean, that's really not needed unless you're doing something crazy, I guess. Okay, and this is the complete formula. We will arrive to this formula in no time. Don't worry about that. Okay, let's get back to our thing. Okay. So conv 2D. So okay. Now let's see NN 2D. Let's run this once. Okay. So this NN2D, it has many arguments. Let's focus on the first 4, that is input, number of channels of the input image, output channel, number of channels of the output layer, kernel size, and stride. I have told you all that means. There are a couple of things to notice here. That is, first, there are no argument for the filter or kernel itself. There is only a kernel size argument, right? The actual filter, that is the square matrix used to perform element wise multiplication, is learned by the module. Okay, that's important to know. Secondly, it is possible to produce multiple channels as output. It simply means that module is going to learn multiple filters. Each filter is going to produce a different result, which is being called a channel here. Okay, so each filter that you have, that I already told you that they are learnables in the network, it will produce different results. Okay, and this are that is what they call as channels. Okay, cool. Works. So you see these numbers are completely different from these numbers, uh, although the shape remains the same, right? But what if we change the output? Now the channel was 1 and the output channel is 2, so we see a completely different shape of it. If I were to show you, okay, this is they are showing the weights of the whole thing. This is what the weight looks like now. It's a 3 by 3 matrix, but there are two of them. That's the point that you should be really careful about. For example, let's see this one, right? This one we had I can also, we can do the weights here as well, right? Weights. Okay, so as you can see, there was one channel. Okay, think of it as, okay, you have this image, right? You have this one image, and you can do a simple convolution on it, right? But what you can do is you can do convolution on multiple of them, right? You can have many more of them, right? So in a sense, out channel is telling us how many of these filters are there. I hope that makes sense. Okay, cool. Applying one filter to it, okay, in a single channel image as input, and applying one filter to it, move one pixel at a time, result in one output per channel. Okay, it results in one output per channel. Cool, works. Now thus results are gibberish now. As of you can see, this results that you see are little gibberish as of now, and yourself, you and our are going to be different in, so sorry, because the convolution module randomly initializes the weights that is represent the kernel. So when the first case, that is this case, when the output channel was 1, there was just one of these guys, right? One of these guys, and the numbers inside them are initialized by PyTorch. All the numbers that are inside are initialized by PyTorch randomly. Okay, that's the whole point of convolution module. It will learn these kernels. These numbers will be the learnables, just like we have in our networks, right? We have these networks, and these are the weights that we have, right? If you remember, blah blah blah, these weights are the learnables in our network, just like that. Now these, and weights in this, and these are just numbers, right? If you remember, we represent them in a matrix, just like that. This is the number that we are going to be learning soon. Cool. Give me a second. Okay, that works. But instead of being, okay, the traditional computer vision, people would develop different filters for different purposes. Like, you can change these filters and the values to have different outputs. Like, you can blur the image, you can sharpen the image, you can find the edges of the image and all that cool stuff by creating these filters all by yourself. You know, you can empirically go and change the values inside it one by one and see what is the output, and then you can come up with an idea. Okay, but instead of being clever and trying to manually devise a filter that does the tricks for a given problem, why not outsource the filter definition to the neural network as well? This way, the network will come up with a filter that highlights features that are relevant to the task at hand. For it is no surprise that the results starting image shown as, okay, give me a second, shown as a grad function attribute. Now you see this, in this one there was no grad function. If you remember, this grad function is telling us this is basically a neural network. Sorry, it's a and required grad equals to 2 kind of a scenario where you have weights that are trainable, and these weights are basically computational graph, and this point is basically the convolutional backward something, right? Like we had that mull backward and subtract backward, right? These are part of a computational graph at this point. Cool. And so I was showing you something, right? Okay, the weights you see here. Now here in this one, you have the output channel as 2, that is creating 2 of these, that is 3 by 3 matrix. And that is the cool part about it. If I change it to 3, then you have 3 of them. Okay, so now this will be convolved. So this filter will be used to convolve on the image and give you one output, and this filter will be convolved on the image and give you another output. This will convolve and give you another output. So if I actually go and check this out, what is the results? um mm, mhm, mhm. Okay, it's showing you we haven't used it to do anything with the image, so we will stick to that. Okay, okay, cool. Okay, as it is a kind of, as we can do now the neat trick that is done here is basically they are learnable weights. What if we keep it in nograd? That is, it will, any operation that's gonna be happening inside this context will not be a part of the computational graph, right? And what you can do is take the that is this convolution, this guy. Okay, let's initialize the kernels, right? Let's initialize the kernels with the weights of our identity matrix. We changed it here. Like, take the weights. If I can show you this, it will be cool. Let's code it out. Take the con and put the weights in, and let's see what it looks like. It looks like this. How about we change? We are taking the first of them. This is the one, and we are completely changing it into the identity. Right? Identity was this guy, right? We are changing that, and we are also taking the bias part of it. We're taking the bias part of it. Take the bias, right? And we're changing the bias into 0 because our this situation that it did not have any bias as of now. So if I do this, if I and then use same, now it is nn.conv2d1, that object, and I'm passing my image through it, you will get the same answer that you got for the f.conv2d1, and that is pretty cool. Yeah. Okay, cool. Yes. Okay. There are 2 filters representing by 3 matrix of the weights. Your values are going to be different than mine, basically, if you run this code. Okay. Even if you have only one channel as input, you can have many channels as output. The filters learned by the network are going to show edges, patterns, and even more complex shapes, sometimes resembling face or a instance. We will get back to visualization of these filters later in this session, right? Okay. To use we can also force the convolution to have the some specification that we just did here, right? Setting the weights is strictly no gradient operation, so you should always use this no grad context, right? Context manager, no grad. Okay, cool, that works. Okay, now striding I already told you what they are. Basically, you take the first one, then jump to the second one if the stride is 2. In our case it is, right? And you get the output of it out of it. Single channel image. Okay, cool. The second step, despite so basically it jumps over it. Okay, after okay, if you can clearly see in this scenario, the output that you get out of it is actually number these this, right? So you can make sense of that. Cool. And this is the formula how this is how the formula will change if you introduce stride into it. That is, it's the same formula from the previous one. Only thing is every single dimension of the output image has been divided by s, that is the size of the stride. In this scenario it is 6, and the stride is 2, so it's basically 6 minus, so I can just give it, okay. In this scenario it was, let's say that's it was 6 comma 6 and convolved over a 3 comma 3 with a stride of 2. We have simply 6 minus 3 plus 1, of course, and divided by 2, right? Both of them will have the same values, right? So I'm not writing the second one. You can get it. What you have is 2 comma, sorry, did I make a mistake? Hmm. So 3 is 4, 6 minus 4 is 2, 2 comma 2, 2 comma 2. So 1 by 1 comma 1, okay. Seems like I made a mistake. Oh, plus 1, right? Is stride equals to 1 in this scenario? If that is the case, it might work. Oh, sorry. Sorry. Stride is equals to 2. Okay. The stride is equals to 1. Stride 1 being it will jump 1 now. So in this case, stride is equals to 1 actually. Sorry about that. So you can see it's 2 by 2. Cool. Yeah. The same. So you see stride equals to 2. What if it's 2? And that is what we get. So you can, here it's defined as 2, but that is how they're defining. If the default one is, I see there's a little difference in the way they are defining it, right? If it's 2, then it's not really a 2 by 2 matrix out of it, because 6 minus 3 plus 1 is 4, 4 divided by, okay, 6 minus 3, oh my god, what am I doing? It's 6 minus 3, that is 3 plus 1, that is 4, 4 and 2 and 2, that is 2 comma 2. That is fine. So stride is basically 2. Sorry about that. Right, and that is that. Let's move along. Padding is basically adding these numbers all around the pixels all around the image, and then you basically add 6, that is 6 by 6 plus 2, because there this one and this one is added on the height of the whole thing. That's a row if you call it, and this part and this part is added on the column part of it, right? That's why that we have that, and the resulting is also 6 by 6. The image was actually this, and we turned it into that. So constant pad 2D is from NN module, and you can use that and do padding on over it. So you can see how padding was added to the original image, right? I hope you can see the zeros. Now you can visualize it, I guess, also. And padded equals to f dot pad. You can add it through f also, and f also. Okay, cool. So padding means stuffing. We need to stuff the original image so it can sustain the attack on its size. Okay. So by adding columns and row of zeros around it, we expand the image such that the gray region starts centering in the actual top corner, top left corners of the image. This simple trick can be used to preserve the original size of the image. And also one more thing is not just that it preserves it, but also if you think about how it's convolving, if it is not using padding, is that few pixels in the middle are getting convolved more than the pixels on the side of the image, right? Think about that. If when we are convolving over the image, the pixels in the middle are getting more focus, because when you are doing this, go through that one by one, right? And these guys will be convolved more than these guys because they are at the side. But if we are using padding, we kind of mitigate that problem a little bit, right? Cool. uh, Nice. We tend to lose information if padding is not applied. You can kind of think of that. Okay, so PyTorch gives two options, that is functional and module. So we already did that. We use functional to create this padding, and then we also use, so there are two arguments: padding for the number of columns and rows to be stuffed in the image, and value for the value that is filled with the new columns and rows. So this value is telling you what value you have to fit inside. If it was 10, then 10 will be added. Okay, and how many padding is telling you how big the padding should be. Oh, that's pretty big. Let's do two. Two is good. Okay, cool, works. Cool. Yeah. Um, One can also do asymmetric padding by use specifying a tuple in the padding argument, left, right, top, bottom. That is what we did here. If I can show you padded, I don't know if it's okay. You can see this. What if I want to change the left guy, right? I want two more on the left. So you see two of them are here on the left. Something like that. Asymmetrically we done that. Mode is constant. So we can stuff. So if we were to stuff our image on left and right side only, the argument would go like 1100, right? That's pretty cool. Cool. So in the functional version, one must specify the padding as a tuple. The value argument is straightforward, and there is yet another argument mode, which is to set constant to match the module version above. Okay. Whereas in CUDA backend, this operation may induce non-deterministic behavior in its backward pass that is not easily switched off. Okay, so it's like if you are using CUDA and all that stuff, there are few behaviors that you cannot replicate, I guess. Replicating padding. Okay, this is like you're using these numbers to get these numbers. Okay, this is reflection padding. I see it's using this 9 and 0 and 7 and 3. Okay, circular padding is using 1 7 6 4. Okay, that's pretty weird. Let's look into that, what they are. Okay, I think replication padding, the padded pixels have the same value as the closest real pixel. The padded corners have the same value as the real corners. The other columns and rows replicate the corresponding values of the original image. I think this is pretty self-explanatory. All I'm going to do is just run this, and you can see it's just taking the value that is nearby, the padded value, right? Now that is done, we can do that using this. We can also do that using f.pad. This is the modes, as I said, the constant padding that we had. We can do it here or there. Okay, padding goes to 1. Reflection padding, let's look at reflection padding. Then reflection padding, it gets a bit trickier. It's like the outer column and rows are used as axis for the reflection. Okay, the outer rows and columns are used as a reflection. So the left padded column, this one, forget about the corners for now. Okay, reflect the second column. Oh, okay. This guy is reflecting this guy. Oh, okay, and this guy is reflecting this guy. This guy is reflecting this guy. Okay, I get that. Okay, that's pretty cool. That is reflection mode. This is circular mode. This is reflection mode. There are a lot of modes, I guess. I can keep playing with that. Okay, circular one. Let's see what circular is. Circular padding, the leftmost or rightmost column get copied as the left right padded column. Forget about the corners for now. Similarly, the topmost row gets copied as the bottom. Oh, okay. This guy here, you see this, the topmost is been copied by this. This guy is coming from here. Okay, I see. I see. I mean, you don't really use it, but cool. And this is, I guess, the formula that you have with everything. You get uh, with padding and the kernel size and the sprites, everything all together is this one, right? Um, okay, you can also see and do the same thing using the padding on the actual um, you know check this out right here. This is the formula from the documentation, right? You, for the height of the image of the output and the width of the image of the output, you simply have the h, that is the height of the, let's say 6, height of the image, and 2 plus, let's say you're adding a padding of 1 as of now, so it will be 1, then minus dilation, we're not adding any dilation, so let it be 0, and sorry, dilation is 1 basically, not 0, and if this is default, dilation is 1 is the default. Okay, and the kernel size is simply your 3 minus 1 and then minus 1 and divided by the whole thing by stride. Let's say the stride is 2. Okay, plus 1. Let's see, 6 plus 2, this minus goes 3 minus 2 root minus 2 minus 2, this will go 3 minus 5, so it's 5 divided by 2 plus 1, that is 7 by 2, and this is floor function, so that will be basically 3. Okay, I hope that makes sense. So 3 is the height and 3 is also the width in this scenario, if that is how we are using it. Cool. Cool. Mhm. If I can show you, I just want to like show you it that once. Is there what all things are there? There are weights and bias. Okay, stride is also there, right? Let's try that out. Padding is, let's say, padding is 1, and what else? You see, it's 3 by 3. That is what we got from calculating also 3. So 3 by 3. Cool. That's fine. Let's go on. Let's move on. Okay. Enough with the identity filter. Let's try an edge detector. Let's create a filter that will actually detect the edges of your image. Okay. So this is your image, right? A single channeled paired image. This is the edge that we have created. I'm going to run that. And we're turning them into a PyTorch tensor. And this is what it looks like. And after convolution with the padding, you got something like this. Okay. Cool. You see 0 into 0 is 0, of course. 5 into 1 is 5, 0 into this, then add all the things inside it, and that will give you 7. That's what it is doing. Convolution part, right? Okay. Cool. As you can see, filters after other than the identity one do not copy, simply copy the value at the center. The element of multiplication simply means something. Cool. Let's apply this filter, and we got the filters, and let's do this. We are padding on the image that this guy, we're padding it, and then padding is constant, the value is 0. We did all the stuff and we did the convolution on it. Let's look at what conv padded looks like. I will just show you this. Yeah, this is what it looks like. That is what we got out of here. Cool. Now let's talk about pooling. pooling is basically you your single channel image is there, right? This is the output that you got here after doing the convolution with one kernel. And you want to take, if pooling is of 2 by 2, you take this 2 by 2 and simply take, if it's a max pooling, okay, there are different kinds of pooling also. So there's min pooling, max pooling, average pooling. If it's average pooling, you'll add this up and divide it by 4. This is basically averaging taking the mean of all the numbers inside this one matrix, and that is your basically min pooling, sorry, average pooling. In this is max pooling, so you will take this one and take the maximum value, that is 22, so you will just put that 22 here, and this is 23, so it will just put that 23 here for in place of this big one. So you would see, if it was 6 by 6 matrix, after doing the pooling you got it, turned it into half. That's what mostly happens, if the pooling is 2 by 2, you will expect that always the image that is coming in will be halved, the size of the image will be halved. Okay, cool. So pooling is different than former operation. It splits the image into tiny chunks, perform an operation on each chunks that yields a single value. Always remember, every single chunk is yielding one values after pooling. So now pooling can be done on, now this is, we are doing it on a 2 by 2 matrix, right? Pooling can be done on anything, a single array also. We can pool it so that it takes the first three, in an array it can take the first three numbers and add them up and give a one number. So pooling always results into a single value, okay, and put the chunks together as a resulting image. Okay. Max pooling with kernel size of 2, that's what you have. The stride is assumed to be the same size as the kernel. Oh, the stride is always at the same size as the kernel, okay, in this scenario. Okay, our input image is split into 9 chunks, you can see it for yourself, and we perform a simple max operation, hence max pooling. And each chunks, really it is just taking the largest value in each chunks, then these values are put together in order to produce a smaller resulting image. The larger the pooling kernel, the smaller the result. That's the trend, right? Larger the kernels, smaller the image, output image, right? Okay, now it can also be done by using both the ways, that is functional and module. Okay, the pooling kernels of 3 by 3 makes the resulting image 1/3 of the size of the original, and so on. So what you see here is, if it's 2 by 2, then it's half. If it's 3 by 3, it's 1/3. If it's 4 by 4, 1/4, right? It is a trend that you can clearly see. If we try a kernel of 4 by 4 in our 6 by 6 image, only one chunk fits and the resulting image would be a single pixel. Cool. Ah, cool. It's 4 by 4 inside this whole thing, right? This thing, only one single will, because it cannot move. The next one will be out of the range of the image, so it will just be just one single pixel if we do 4 by 4 in this case. Okay. But if it was a, think of this, it was a 16 by 16, right? If it was, then if we do a 4 by 4 pooling on that, you will get a 4 by 4 matrix out of it. Cool. So there are two ways using functions. So you are passing the con padded, this one, right? This is 6 by 6 and the kernel size is 2. You got this guy, that is exactly what you see on the image on the top. You can use NN module also. Now the kernel size here is 4 and you just got a single value. So you can check this, taking this one, and what is the biggest value? Yeah, 24 is the biggest value, just gave that. Okay, and max pooling kernel is 3 and stride is 1. Okay, if the stride is 1, then this is what you are getting out of it. That is, taking this one, kernel is 3, kernel size is 3 actually, just bigger. So it's this whole thing and then this whole thing and this whole thing and this one. That should be 2 by okay. Oh, stride is 1. Stride is 1. So it's like taking this one first, and which is the biggest one is 24. then taking this one, that is also 24. In this case, it's 23. In this case, also 23. So can I say 24, 24, 23, 23? Yeah, that works. Hmm. So can they, are there other pooling methods? Yeah, of course, there are average pooling. That is most commonly used. Name suggests is just take, it will output the average pixel value for each chunks. In PyTorch, we have f dot average. You can do that as well if you want to. I'm not doing it. Let's see what flattening is. Take this value, right, the pooled value here from here, and flatten it. So basically take all of them and all the rows and turn them into a single row. That's what happening here. Or you can do it simply by using view. Okay, that is that. I don't think I need to explain you what that is. Okay. So we perform convolution padding pooling in two dimensional because we are handling images. But there are 1 and 3 dimensional versions of the some of these as well. That is nn dot, con 1D, con 2D, and so it can be like con. So you see, this all of them are con 2D. Say con 2D. There are con 1D also. There are con 3D also. Okay, constant padding 1D also, constant padding 3D, constant padding 1D, 3D, everything that you saw for 2D, we have it for 1D as well. Okay, we will venture into 3D dimension, but we will get back to one dimensional operation later. Okay, aren't images 3 dimensional since they have 3 channels? Well, yes, but we will still be applying 2 dimensional convolution to them. We will go through the detailed example using 3 channel images in the next parts. Okay, typical architecture. The typical architecture uses a sequence of one or more typical convolutional blocks, with each block consisting of 3 operations. You can clearly see, let's see. Okay, this is the architecture, how it goes. This is the image, that's a 3 by 3 image, just one image. Okay, sorry, 32 by 32 image. It's a layered architecture by Lev. Yeah, the I think the scientist at Meta, Le Yukang, some Lukang, I don't remember his name exactly. I mean, you can see the reference to the paper right here. Okay, so this was I think the first architecture that was built on CNN and kind of proved really great, right? So you have now 6 kernels of 28 by 28. Okay, then you do max pooling on them. So you see literally half, 28 half is 14, right? So it literally half. I told you, if you want to pooling, if the size uh so if your max pooling size is 2 by 2, then it will just half it, right? That's what happened here. And then you are taking another 16 of the kernels, that is filter size, and you're putting the size to be 10, right? And you get 16. So you see there are 6 kernels or filters. I'm just going to call them filters from now on. So you have filters, 16 filters taking the same image. Okay, so one filter is taking one image and spitting out one image. The other filter is taking one image on the same image as exactly and spitting out. So this one image is convolved over all these 6 and it gives 6 outputs. I hope that makes sense, right? Here in this scenario, if you see after the pooling and stuff happens, you have these 16, right? These 16 images. And what you see here clearly is, um, okay, convolution happened here and you got this when you're pulling it. They haven't really specified the convolution size. Let's see, let's build the whole thing, that then that will make more sense, I guess. Okay. Hmm. Okay, let's go through it one by one. Okay, okay. Let's build a model out of it. Okay. So the first, we are creating a sequential model and it looks something like this. The first is the channel is 1 and the output channel is 6. So, and the slide is 5. This is 5 by 5. Okay. And you see that is what happening here. It's a 5 by 6 by, 5 by 5 kernels, right? And there are 6 of them. That's why you have 6 output out of it. And then you are applying the activator function into it. Now the next is pooling. So this is the first kind of a block, you can call it, right? And you're pooling it and you got the answer, right? In this scenario, the block is coming in, so it's 28 and it's converted 28 and this is coming out of it. So after this block you have a image. There are 6 images, 6 filters, you can, six features, and every feature is 14 by 14. Okay. uh, and then now take this features and put it in second block. Second block saying that there are, of course there are 6 features, right? So uh, 6 channels coming in, so 6 of them are there coming in, and you are projecting into 16 filters are there, and that's why you get a 16 output here. You see 16 output, and every one is 10 by 10, and this 10 by 10 you can actually find by the formula that I have told you, if right. um, cool. And you have, then you add the ReLU and also then the max pooling. So after this what you have is this 14 by 14 goes to 10 by 10, and after the max pooling it becomes 5 by 5. Now there are 16, you can think of it as 16 images, but in the sense it's 16 channels exactly, even, right? And there every single feature is of 5 by 5. Okay, 16 images, that's, and they're 5 by 5 in a sense. Okay, now the third block coming in, it takes this 16 images, and then the output channel is of 120. That is pretty big, right? And you simply take that and it will spit out 120 of the images. So this was 5 by 5, right? 16 images of 5 by 5, and you're taking it into one single image now of 120. Okay, 120. Cool. And the stride is also 5 by 5. That's why. Uh, and then you simply flatten it, and I guess here flattening is happening, and they take the 6, and you basically once the flattening has happened you are putting it into a feed forward network, a simple fully connected feed forward network. From this is basically a normal network that we have like ANNs, 120 inputs, then this is the hidden layer, and this is the output, right? There are 10 outputs. So right now what I think we are trying to do is do some classification you on the MNIST dataset. Now MNIST dataset is the handwritten dataset of letters of numbers from 0 to 9. So you have 10 outputs, and that's why we have output as 10. Okay, I can break this down even further actually, but I don't want to go too deep into it. I think someone, all that we are trying to do understand is how PyTorch is implementing it. Okay, cool. So now let's see what does lanenet looks like. State, I mean it's gonna be a big stuff, I know. There's a lot of things happening here. If I can use this torch summary, right? I can torch. Give me a second. Forgot the code for that. Torch info. Yeah, torch info was right. You have the model. You can use this. Let's do this. Connet. No, we are not doing that. We are using this guy. Just passing it here. Let's say batch size is 1 as of now. And input is 32 by 32, right? 32 by 32. The image coming in is 32 by 32. Okay, seems some kind of a problem. Please about track information. I guess it's 28 by 28. Yep. Okay. Hmm. That is what we see here. You can see clearly after this whole block, sequential block, you get 1 comma 10, one image, and we are seeing which one is the most probable from 0 to 9. Okay, 0, that's why we have 10 outputs out of it. So you are taking the first dude is doing 0 1 6 28 28, and the number of parameters is ordered, so there are 61,000 parameters in this one. That's pretty big for what we are doing from before, right? Yeah, ReLU does not do anything, but pooling does, right? And then goes to the second block. It is taking the uh yeah, yep, kerneling and all that stuff happens. Okay, yeah, cool. Multi-class classification problems, data generation. Data has been generated. Do this. Let us see what's happening here. Mm-hmm. Okay, if you remember, we were doing this. I mean, we can take this to the next, next session, multi-class classification, because right now what we did before was do is it diagonal or not? That's the classification that we did, but we can also do if it like is it parallel, horizontal or vertical, that becomes one label. Is it diagonal, tilted to the right, can be another label, and it's a diagonal tilted to the left, can be another. So this, if it this is tilted to the kind of to the right, then it's one. If it's tilted to the left, then it is two. Okay, so and this is zero, so there are three labels as of now, and we can do that too. So we will get to that in the next session. I will also go through a little bit of what is this, and I can do that here itself. But go through the layenet architecture. Basically, it was used to classify the MNIST dataset. That is the dataset of handwritten digits, right? Okay, then see you in the next session. Thank you.